to my YouTube channel. I'm trying to keep up with that. I'm doing a decent job, I think. All right. Organic Chemistry 1, Chemistry 3101. This is Chapter 6, Chemical Reactivity and Mechanisms. And let's start off with a tiny bit of review, and we're going to cover the definition of what enthalpy is. And hopefully you remember enthalpy. We use the variable H for enthalpy. So we have delta H, which is change in enthalpy, or Q. And I'm going to explain why we can write it as delta H or Q in a second. But enthalpy, it says, is the heat energy exchange between the reaction and the surroundings. And it's important that you remember that it is at constant pressure. And in organic chemistry, we run, I'd say 99%, if not more, of our reactions at constant pressure. What does that mean? It means that even if you're running the reaction in some kind of reaction flask like this, it's usually going to be open to the atmosphere. Now, it might not be directly open to the atmosphere. You might have, a drying tube, which is something to prevent water from going in, but it doesn't prevent gases from going through. It doesn't prevent oxygen and nitrogen from the atmosphere from going in and out. We have sometimes a drying agent in a drying tube. That's neither here nor there, but the idea is that most of the time we run reactions at constant pressure, and enthalpy is the heat exchange between our reaction and its surroundings at constant pressure. Well, let's move on from there and talk a little bit about how electrons achieve a lower energy state when they occupy a bonding molecular orbital. Remember that when we form a covalent bond is formed by the sharing of two electrons in atomic orbitals. And when those two electrons come together to make a bond, what do? They go from the atomic orbitals down into a bonding molecular orbital. And if they go into a lower energy state when they're in that bonding molecular orbital, well, it stands to reason that bond breaking, if we want to break any kind of bond, whether it's a sigma bond or a pi bond, whatever, any kind of bond, is going to require some input of energy. Right? That is just something you got to have in your mind. If I want to break a bond between two atoms, a carbon and a hydrogen, two carbons, a carbon and an oxygen, it's going to require energy to break that bond. So the electrons must absorb kinetic energy to overcome the stability of the bond. All right, it takes energy to break a bond. Well, let's move on from there, and let's talk about the ways that bonds can break. There's a couple of ways that bonds can break. They can break what are called homolytically and heterolytically. You need to know the difference between the two. When we have homolytic bond cleavage, what that means is that the bond kind of breaks evenly, so to speak, and each atom takes one electron. And so you end up with a pair of radicals when you have homolytic bond cleavage. When you have heterolytic bond cleavage, you could probably guess that one atom takes both of the electrons, and we end up with a pair of ions. We end up with a cation and an anion. And the bond dissociation energy, or the delta H for bond breaking, corresponds to homolytic bond cleavages. And so from now on, whenever we talk about the delta H for a reaction, and I'm going to bring up bond dissociation energies a little bit with you today, whenever we do that, we're always talking about homolytic bond cleavage. Okay, always talking about homolytic bond cleavage. So we're always going to be referring to this guy right here, breaking the bond and ending up with a pair of radicals. Well, before we look at a table of bond dissociation energies, how much energy does it take to break a bond? I want to go over to a blank document with you here just for a second and go over a little bit of background with you on enthalpy. So enthalpy, or H, and then if we talk about change in enthalpy, we talk about delta H. Well, something that you might remember from General Chemistry 1 or General Chemistry 2 is that energy, so energy, for which we use the symbol U, is equal to heat plus work. Now, that's something that you should have seen in your general chemistry days. And so if we're trying to determine what the change in energy is, delta U, our change in energy, we say that's going to be equal to Q subtract the negative of P delta V, because we remember that work is pressure volume work. And again, this is something that you should have seen in general chemistry. The W, or work, is equal to the negative of delta PV. And we can scribble that in here, negative delta PV. All right, so that's what we've got so far. Now, another thing that you would have seen is the definition of enthalpy. So enthalpy, or change in enthalpy, I'll write it like this: change in enthalpy, delta H is equal to delta U plus P delta V, like that. So now what we're going to do is we're going to take our definition of what delta U is, and we're going to substitute it in here. Look what happens when we do that. We end up with delta H, delta H is equal to Q minus P delta V plus P delta V. Well, we have negative P delta V and we have positive P delta V, and so these two cancel out, and we get that delta H is equal to Q at constant pressure. Notice we're not talking about delta P, we're only talking about a constant pressure. So delta H is equal to Q at constant pressure. And so again, that is our definition of enthalpy in organic chemistry, because we almost always run our reactions at constant pressure, and that's the only thing that we're going to be discussing in this course, is running reactions at constant pressure. And so if we go back to our lecture slides, we go back here, we see that delta H, we can also define it as Q. And so that's a little bit of review of where that comes from. Well, let's talk about these bond dissociation energies. How much energy does it take to break a bond? Look at the amount of energy that it takes to break a hydrogen bond, a hydrogen bond. So this would be an H2 molecule. And if you want to break that homolytically, it would take 435 kilojoules if you had 1 mole of hydrogen. What if you had the carbon-hydrogen bond in methane? Well, then it takes 435 as well. What if you had the carbon-hydrogen bond in ethane? Then it takes a little less energy. Here we have all the halo acids. We have HF, HCl, HBr, and HI. And you can see that as you go down, generally speaking, or actually as you go down the group, it costs less energy to break those bonds. We have some carbon-carbon bonds here as well. We have the carbon-carbon bond in ethane. So this is ethane here. Then we have propane here. We have isobutane here. Anyhow, you do not have to memorize any of the values in this table. Okay, you don't have to memorize any of the values whatsoever. However, you do have to know how to use bond dissociation energies. And so if you look at table 6.1 in our textbook, you can find a whole holy host of bond dissociation energies in there. Again, you don't have to memorize any of them. If you want to, go ahead. That's not a problem, but it's not something that we have to do. And I'm going to show you how to use bond dissociation energies to calculate the change in enthalpy for a reaction at constant pressure this morning. That's something that we're going to go over today. Now, this is a table I took from another book. So I got this from it's another publisher's textbook. But there are some things I want to point out in this table that is a more exhaustive table of bond dissociation energies. Namely, that as we go from a single to a double to a triple bond, we see that we have an increase in the bond dissociation energy. Check this out. If we have a carbon-carbon bond, which is found right here, we see that it costs around 347 kilojoules per mole to break that bond. Whereas if you have a double bond, then it costs almost twice as much energy, and a triple bond is almost 3 times as much. And that goes along with what we talked about earlier on in the class when we just started kind of quickly qualifying really the difference between a carbon-carbon single, double, and triple bond. We said that as you form more bonds, you have more orbital overlap, and therefore it requires more energy to break the bonds. Also notice another trend exemplified in this table, something that we saw previously, that bond length decreases as we go from a single to a double to a triple. And I'm sure that somebody's even ahead of me here and has already discovered that if you look at a nitrogen-nitrogen single bond versus a double versus a triple, you see the same effect there, that as we increase the number of bonds, not only do we see that it requires more energy to break the bond, but we also see that the bonds become shorter. So again, a more exhaustive table. No need to memorize any of these. We're going to be using table 6.1 most of the time. So let's review a little bit here. It says most reactions involve breaking and forming bonds. The total change in enthalpy is referred to as the heat of reaction. Okay, so again, delta H is equal to Q at constant pressure. And so since Q represents heat, we can say the change in enthalpy is equal to the change in heat for the reaction. Well, something else you need to know are exothermic and endothermic reactions. What are the differences? And what do they mean? And usually students are pretty good at this. I think that exothermic, there's a lot of clues in the word. You know, people think of thermic, they think of temperature. And whenever I hear of exo, I think of leaving, like exiting a building, and that would be a, you know, perfectly reasonable assumption to make. So exothermic means heat is released, or we could say energy is released by bonds in the form of heat. So it says here, the energy released by bonds exceeds the energy needed for the bonds to be broken. So that's an exothermic reaction. And in an exothermic reaction, the products are going to be more stable than the reactants. Now, if you're thinking, I remember looking at diagrams, like these little graphs that showed you exothermic and endothermic reactions. We're going to look at those in just a second. Before we do, let's talk about an endothermic reaction. You can probably guess it's the opposite. Energy is required for bonds broken, and that exceeds the stability of what's gained by the bonds that are formed. And so when we're dealing with an endothermic reaction, the products are going to be less stable than the reactant. So let's take a look at a graphical representation here of an exothermic versus an endothermic reaction. So we'll start with exothermic over here. Let's see, we have our starting materials. Let me get my yellow highlighter right here. We have our starting materials and we have our products. And we see that our products are more stable than our reactants. Products are more stable than our reactants. And you might remember a formula that you would have used to calculate the delta H for a reaction that you would have seen in General Chemistry 1, probably in your thermochemistry chapter. You would have said delta H naught, which just means a standard condition. So delta H naught for your reaction is equal to the delta H of formation of your products minus the delta H naught of formation of your reactants. And that gives you the delta H for your reaction. Again, this is something that you would have seen in General Chemistry 1 and also in General Chemistry 2. So let's think about this formula. If it's products minus reactants, well, if you look at the y-axis here, okay, so we're going from a low number to a high number here. Okay, so if we're dealing with an exothermic reaction, that means we're starting with our products, which are at a lower value. So we're taking a small number, and we're subtracting something that's higher in enthalpy. So we're subtracting a big number. If you take a small number and you subtract a big number, what do you get? You get a negative number. And so our delta H is going to be negative for an exothermic reaction. Our products are lower in energy. The energy is released as heat. Why does that happen? Well, it happens because the potential energy stored in the bonds is converted into kinetic energy, and the temperature of the surroundings increases. So the particles that are surrounding the reaction vessel are going to start moving faster, and so their kinetic energy and their temperature is going to increase. Well, if we take the same rationale and examine the reaction coordinate diagram for an endothermic reaction, we take the same rationale. So I'm just talking about this formula right here. And we have our products minus our reactants. So our products are at a higher value. So now we're taking a big number and we're subtracting a small number. And if you take a large number and subtract a small number from it, you end up with a positive value. And so the delta H for an endothermic reaction is a positive value. The products are higher in energy. Energy is consumed. So we take the kinetic energy from the surroundings, and it's stored in the potential energy of the bonds. And of course, the temperature of the surroundings is consumed, or it decreases, it goes down. All right, there we go. So that's a little review on endothermic and exothermic. And can I get a thumbs up on that? Is everybody with me on endothermic and exothermic so far? Okay, and then again, just a review. Again, you would have seen this in General Chemistry 1 in your thermochemistry chapter, but I know that you all passed General Chemistry 2. That's guaranteed. And you would have studied thermodynamics in that course, and you would have seen exothermic and endothermic reactions there as well. Well, let's take a look at something a little bit different here, and let's try a practice problem. So let's go back here. And it says, using the data in table 6.1, predict the sign and the magnitude of the delta H naught for the following reaction. So we're trying to calculate, delta H naught for the reaction. Identify whether the reaction is expected to be endothermic or exothermic. So what did I tell you on the last slide? Well, I'm going to write out the more complete form of the formula, the form of the formula that you would have seen in General Chemistry 1 and 2 that you use probably most of the time to calculate the delta H of the reaction. So maybe, let's write it like this. So we've got the sum of the stoichiometric coefficients multiplied by the change in enthalpy at standard condition. So the heat of formation of the product, so I'll put here products minus the delta H of formation of the reactants. So this, again, is what you would have seen in Gen Chem 1 and 2. We are not going to use that formula in this class. Now, why wouldn't we use that formula? Okay, so if you're not fully awake, just wake up for 1 minute here and I'll try to explain it. The reason why we're not going to use this formula, and there's nothing wrong with this formula, it's a great formula. I use it all the time in general chemistry. It's because what you did is you would go into the appendix of your general chemistry book and you would look up the heat of formation of a compound in that book, okay? And in general chemistry 1 and 2, you're dealing with a much smaller number of compounds. You deal with a lot of inorganic compounds. And so they're able to build a table that has got enough delta H of formation values in it that you can just go in the table and look up the compound. The problem is, and you probably can look up the heats of formation of many organic compounds, but there are so many organic compounds that we usually, and in this class, we're always going to use a different form of this formula. So let me show you what we're going to use. What we're going to use is this. We're going to say delta H naught of our reaction is going to be equal to the bond dissociation energy of the reactants, so BDE of the reactants, subtract the bond dissociation energies of the products. Okay. Now notice that in this formula, it's products minus reactants. If you think about, go back to your general chemistry 1, go back in the recesses of your mind. When you calculated delta G naught of a reaction, if you calculated the delta S, of a reaction, it was always products minus reactants. This, my friends, is the only formula you're ever going to see in any chemistry class, unless there's something in the 3000 level and above. It's the only formula you're ever going to see that's reactants minus products. And I'll explain why it is that in a second. So what we're going to do is we're going to look at all the bond dissociation energies for our reactants, and then we're going to subtract the bond dissociation energies of the bonds formed in our product. So let's examine this in a little more detail and take a look at what's really going on here. So we have this reaction between propane and bromine, right? If we just have 3 carbons, that's just plain old propane. We're combining it with bromine. We're making this compound, which is 2-bromopropane, and we're making HBr. So let's talk about bond dissociation energies of our reactants. And so we're looking at bonds that are broken, right? Because our reactants, we're going to have to break some bonds. What are the bonds that are being broken in our reactants? Here are our reactants, propane and bromine. Well, if we're putting a bromine on the propane, that means that I have to break one of the carbon-hydrogen bonds in the middle of propane at the CH2, right? There's 2 hydrogens here, but I'm just going to draw in one of them because we need to break that bond. And also, we need to break the bond between the 2 bromines in Br2. I'm just going to draw the full Lewis structure just to get the point across that we're breaking this bond and we're breaking this bond. So bonds broken. Now I went ahead and I looked up the values in table 6.1. Now I don't know, because I don't have the exhaustive table here. I don't have the bond dissociation energy of the carbon-hydrogen bond for the methylene in propane. However, I don't even have it for bromine. So if you go to the table in the book, you'll find the values Okay, I promise they're in there. So let's take a look. The bond dissociation energies of our reactants. So this bond has a bond dissociation energy of 397 kilojoules per mole. That's how much it takes to break 1 mole of that bond. So let's put in here 397 kilojoules per mole. And then the bond dissociation energy of the Br2. I looked that up, and the amount of energy that it takes is 193 kilojoules per mole. Okay, so 193 kilojoules per mole. So what we're saying is that it takes 397 plus 193 kilojoules total to break 1 mole of each of those bonds, okay? If we combined, the two of them together. So now we've got bonds formed. This is going to be our bonds formed. What are the bonds that are formed? Well, one of them is the bond between the carbon and the bromine of propane, of the carbon in the middle. And I said the word methylene. Whenever I talk about a CH2 like this, that's called a methylene. So instead of me always calling it a CH2, I'll call it a methylene. And I looked up that one. It's 285, so 285 kilojoules per mole. And then the amount of energy that it takes to break an HBr bond, which I also looked up, it's 368. So 368 kilojoules per mole. And again, these values all come from table 6.1. I just didn't put the entire table in the slides. So let's pencil that in. So we've got our bonds formed. So, sorry, I didn't have a negative sign in there. I put a positive sign. That's not right. So subtract the amount of energy from the bonds formed. So what have we got here? We've got our carbon-bromine bond, 285 kilojoules per mole, plus 368 kilojoules per mole, like that. And if you think about what's happening here, let's take a look. You're starting out by adding 397 plus 193. Why? Because those are the bonds that are broken. You have to put energy in to break the bonds, and therefore it's going to be a positive value. Why do we have a negative sign here? It's because when bonds are formed, energy is released, right? We can think about this side of the equation as energy. We can think about this side as energy in, and we can think about this side as energy released. And the released comes from the negative sign. So the energy is released in this part. And so when you tally all that up, you get that the delta H naught for the reaction is equal to negative 63 kilojoules per mole. And so this reaction, would it be endothermic or exothermic? Could anybody answer that for me? This be an endothermic or an exothermic reaction? Yeah, absolutely. So this reaction is exothermic. Now, if you're watching me solve this problem and thinking, holy smokes, Mr. Dion, all I had to do is look up the bond association energies in table 6.1 and then just plug them into this formula right here. I could have done that much faster than you. Well, remember, I'm trying to explain it as I go along. But yes, that's all you have to do. And I repeat, you do not have to memorize any of the values. If you need them for a quiz, I will give them to you. If you need them for an exam, I will give them to you. Okay, so no need to memorize table 6.1. Well, what's interesting about enthalpy is, you think about an exothermic reaction, one where heat is released. What's a reaction that you can think about in your everyday life where heat is released? Could anybody give me an example? I got one major example. What's a reaction or something that you see in everyday life where it's a chemical reaction where heat is released? Could anybody give me an example? What about a combustion reaction where we burn something? Right, if you make a campfire, and I hope you've made a campfire at least once in your life. If you haven't, you should try it. But let's say we make a campfire and we burn some wood. Well, heat is being released. Right, you think about it, you start the fire and then you just keep adding wood to it and it keeps burning. And so, you think, well, an exothermic reaction is a spontaneous reaction. And there are many reactions that are spontaneous and are exothermic. However, we can also have endothermic reactions that are spontaneous. Really, we can. You know, with the energy of the products is higher than that of the reactants, but it is spontaneous. You know, it can happen. And so, what am I getting at? I'm really kind of trying to make a segue to section 6.2, which deals with entropy, because the ultimate deciding factor as to whether a reaction is going to happen or not is based on delta S, or entropy. Check it out. It says here at the top that exothermic and endothermic reactions, so exothermic is where the delta H of reaction is a negative number. This is the little sign I use for negative. And if we have an endothermic reaction, the delta H of our reaction is positive. So this is the little sign I use for positive. Both of those can occur spontaneously depending on the situation. And so in order for us to determine whether a reaction is going to be spontaneous or not, we have to take into account both enthalpy and entropy. Okay, we've got to examine both of those things. And I know that many of you are ahead of me and are already thinking, yeah, no problem. I got it, Gibbs free energy. But before we get there, let's talk about entropy a little bit more. And I want you to remember that entropy can be described as molecular disorder, randomness, or freedom in a process that involves an increase in entropy is one where our delta S is going to be positive. Right? Think of entropy as molecular disorder, randomness. You know, think about, I always think about a messy bedroom. If you listen to any of my old videos, I probably always bring that up. Entropy is, spontaneous, right? You think about, I'll clean up the kitchen or something. It just becomes random and messy spontaneously. It seems like it requires no energy to do that whatsoever. However, to make it ordered, that takes a lot of energy. Oh boy, does it ever. And you have to clean the kitchen. Well, let's talk about the two most dominant factors affecting entropy in organic chemistry. What do we need to consider as Chemistry 3101 students when we're talking about entropy? Well, two main things. Number one is when there's more moles of product than reactant. Okay? If you're starting with 1 mole of something and then you break it apart and you end up with 2 moles or more of something, well, then your delta S is going to be positive, right? The randomness is increasing. You think there's only one way to put A and B to organize it. It's as A and B. Whereas A and B, if they're separate like this, then there's more than one way that I can organize them. Okay, so they're more disordered. And the other way is when a cyclic compound becomes acyclic. So if you have something that's a cycle, like maybe a cyclohexane or something, and then you break it open, okay, well, then it has more freedom of movement, so to speak. And so our delta S would be positive for that. Give me a thumbs up if you're good with me on this slide. Just the whole idea that if we go from one thing to two things, entropy is increasing. And if we go from one thing that's cyclic to something that's acyclic, entropy is increasing. Cool. Usually students don't struggle with this, but the idea is that both of these result in an increase in disorder or delta S. Same thing, disorder. There we go. Well, with both of those things in mind, let's take a look at a question. It says here, for each of these processes, just tell me what the sign of delta S is, okay? In other words, is delta S of this system going to be positive or negative? So we'll start with the one on top. This reaction is something that we do in organic chemistry too. You don't need to know this at all, but this is called a Diels-Alder reaction. It's named after two organic chemists, and he had the Diels-Alder reaction, and they won the Nobel Prize for this reaction. That's neither here nor there. But could anybody tell me, would the delta S be positive or negative for A? Positive or negative delta S? Yeah, absolutely. Anybody else have an answer to that one? I see that somebody wrote in the chat that the delta S is negative, and they'd be absolutely correct, right? Because we're going from two molecules to one molecule. So, or you could say we're going from 2 moles of reactants to 1 mole of products. Either way works. All right, so our disorder is decreasing. And what about the next one? Down here, we have this compound. This is called tert-butyl bromide. And then we end up with this carbocation and a bromide ion. What's happening here? Is my delta S positive or negative? Yeah, absolutely. Like delta S is positive, right? Things are the randomness or the disorder is increasing as things get more disordered. We go from 1 mole of something to 2 moles of something. Okay, so that covers the first two sections already done. Covered enthalpy, what that means, the heat of reaction at constant pressure. The change in enthalpy for a reaction is the delta H of a reaction. We can calculate it using heat of formation values that we would get from a table, like you did in General Chemistry 1. But in organic chemistry, we use bond dissociation energies. And so we use the formula that the delta H of a reaction is equal to the bond dissociation energies of the reactants minus the bond dissociation energies of the product. So that's what we covered in 6.1. 6.2, we said, well, whether a reaction is endothermic or exothermic, that's not the ultimate deciding factor as to whether or not a reaction will be spontaneous. In order for us to determine that, we have to look at entropy. And so now we've defined entropy, and we said the two most important scenarios, they're represented on this slide. Go from 2 molecules to 1. That means our delta S is decreasing. If you go from 1 molecule to 2, our delta S is increasing. And I guess the other one isn't on here, which is going from a cyclic compound to an acyclic. Well, your delta S is increasing. Well, again, going back to your general chemistry days, you can see I talk a lot about general chemistry in chapter 6. And I'll try to stop once we get to about halfway through the chapter. But now that we've covered these things, you would remember that Gibbs free energy, delta G, is what we use to determine whether a reaction is spontaneous or not. And if you're thinking, well, Mr. Dion, 2 minutes ago, you said it was based on entropy. I did. It Gibbs free energy is nothing more than a repackaged version of total entropy of the system and the surroundings. If you don't remember general chemistry, let's review. So recall, the spontaneity of a process depends on total entropy. What's total entropy? Total entropy is the sum of the entropy of the system. That's the entropy of our reaction, and the change in the entropy of the surroundings. And the surroundings is the environment surrounding the reaction. So we could put here environment. Okay, whatever. All right. So delta S of the system can be measured, or it can be estimated using the values from a table. And you would have done this in general chemistry. You would have calculated the change in entropy for a reaction just going into the appendix and looking up some values. Cool. Everybody could do that. The delta S for the system is equal to the S value for the products minus the S values for the reactants. Okay, that's neither here nor there. Then the delta S of the surroundings, well, it's kind of hard to measure the change in entropy of the surroundings. I mean, how do you go around a reaction flask and determine how disordered the environment is around it? But luckily, we have a workaround for that, and that is that the delta S of the surroundings, or the change in disorder, entropy of the surroundings, what's surrounding the reaction, is equal to the negative of the delta H of the system divided by temperature. Now, we don't go into the where this formula comes from. We don't even cover that in general chemistry 1 and 2. But what this does is it enables us to plug this as our definition for the delta S of the surroundings, and we get this new formula, which is shown here at the bottom, delta S total. So the total change in entropy, which is going to be the ultimate deciding factor as to whether the reaction is spontaneous or not, is equal to negative of the change in enthalpy of the system over temperature plus the change in entropy of the system. And now we've defined the total entropy, again, what is going to govern whether the reaction is spontaneous or not, totally in terms of the system, only based on the system. And so we can get both of these, quite easily. And so now what we're going to do is we're going to take this entire equation here and we're going to multiply it by negative T. What happens when we do that? We get this formula. We get negative T times the total entropy is equal to the delta S, delta H of the system, subtract T, which is an absolute value, right? Because T, or I shouldn't say absolute value, it's a positive value because T is in Kelvin, multiplied by the delta S of the system. And so again, this term here, negative T multiplied by the total entropy, is what we call Gibbs free energy, or the change in Gibbs free energy is delta G is equal to delta H minus T delta S. And this is a formula that I bet, was given to you maybe even on an exam, but I bet you have that somewhere in the recesses of your mind. Now, if the total entropy, system and surroundings, is increasing, right, we'd say that's a spontaneous reaction, but you're taking a positive number and you're multiplying it by negative T. So that means that when delta G is a negative number, our reaction is spontaneous. And when delta G is a positive value, it means that our reaction is non-spontaneous. Here's just, some text that tells you what I just said a couple of seconds ago. Gibbs free energy is nothing more than a repackaged way of expressing total entropy. Who remembers this formula? Give me a thumbs up if you're like, I remember this formula. I saw this somewhere. I tried to forget it, but is everybody with me? Oh, sorry, I can't see my students. Okay, cool. Yeah, totally, something that you would have covered more so in general chemistry. Actually, you would have covered it in general chemistry 2 and general chemistry 1. But anyhow, there we go, Gibbs free energy. Well, let's take a look at Gibbs free energy in a little more detail, and then we'll move on to something new. But let's get at it here. It says Gibbs free energy. What we're going to do now is we're going to look at exergonic and endergonic processes. So if a process has a negative delta G, remember that it is a spontaneous process, and we say that it's exergonic. Notice that in this reaction coordinate diagram where we have free energy on the y-axis, we have our reactants and products. And if you use the formula that you would have learned in general chemistry, and I'll write it down here, delta G of our reaction is equal to the sum of the changes in Gibbs free energy of the formation of our, I'll just write here, of our products minus the sum of the stoichiometric coefficients multiplied by the delta G of our reactants, like that. And so here we have our products being a small number, our reactants being a large number. And if you take a small number and you subtract a large number, what do you get? You end up with a negative number. So exergonic reaction, spontaneous, delta G is negative. I'm not going to rewrite this formula, but I'll refer to it over here. When we have an endergonic process, our delta G is going to be positive because we're taking a large number and subtracting a small number. And so this would be a non-spontaneous process. An endergonic process is non-spontaneous. Are you with me so far? Give me a thumbs up if you follow me up to this point. Do not hesitate to interrupt me if you have a question at any point. I'd be more than happy to address any questions. So where are we? It's, we've been in class for a while here. We've already covered the first 3 sections. So what did we talk about? Section 6.1, enthalpy. The next section, entropy, and now we've covered Gibbs free energy. And Gibbs free energy is just a way of describing total entropy in terms of the change in enthalpy of the system and the entropy of the system. Well, let's move on and let's talk about equilibria. And I know that equilibria is something that you would have done an entire chapter on in general chemistry 2. I know that everybody here would have learned how to determine a reaction order using the method of initial rate. So if you remember this whole thing, rate is equal to K multiplied by, change in concentration. Well, that's something that we're going to look at later. But I know you would have covered equilibria in there, and you would have looked at equilibrium constants like KEQ. So I know you would have looked at KEQ in that chapter. So again, we're going to get into kinetics in a little bit, but let's focus on equilibria right now. So let's say we've got an exergonic process like the one that's here. And the question we want to ask ourselves is, delta G is negative. There's no arguing that. It's an exergonic process, but is every single molecule of A and B going to be converted into products? And the answer is not necessarily. It could happen, but usually, most of the time in organic chemistry, we're going to be looking at reactions where that's not going to happen, but an equilibrium will be reached. So a spontaneous process, all it means is that you're going to have more products than reactants. It doesn't mean that every molecule of reactant is going to get converted into products. There are situations where that can happen, but we're going to look at many situations where that doesn't happen. And thus, based on those first 2 points, the conclusion that we can make is that the greater the magnitude of delta G, so the more negative it is, the more products we're going to have. And I actually have that represented in a table that we're going to look at in a second. Now, if you're thinking, well, if the reaction is spontaneous, if it's exergonic, why doesn't it give us just 100% products? Well, the answer is because as the concentrations of A and B decrease, what's going to happen is we're going to have less frequent collisions occurring between A and B, right? We're starting over here with only A and B. And we see that our change in free energy is negative, right? Our slope is negative over here, so the reaction is spontaneous. But what happens if we're going in this direction, the reaction is decreasing in free energy, it's spontaneous. What's happening is look at the concentration. The concentration of A and B is decreasing as we go in this direction, and we're getting more C and D, okay? But as C and D start to increase, then the collisions between C and D are going to occur more frequently, right? So as we start to make more C and D, we get collisions between those. And eventually you reach something, a minimum value of G, where the rate of the forward reaction is going to be equal to the rate of the reverse reaction, and we call this equilibrium. Again, it's a definition that all chemistry students need to know, that equilibrium is achieved when the rate of the forward reaction is equal to the rate of the reverse reaction. And this point, where the hell was I? Oh, come on. Where was I? Over here. Yeah, this point I'll put right here at the bottom. I mean, this is a very particular concentration of reactants and products. And you might remember the formula that K equilibrium is equal to the concentration of the products divided by the concentration of the reactants. All right. Well, let's move on from here. It says that an equilibrium constant, or KEQ, big K, uppercase K, is used to show the degree to which a reaction is product or reactant favored. So let's think about this. If we have products in the numerator, if you have more products than reactants, what's K going to be? Is it going to be greater than 1 or less than 1 if you have mostly products? Did anybody answer that? If you have mostly products, what will K be? Would it be greater than 1 or less than 1? If your numerator is bigger than your denominator. Could anybody answer that? Yeah, absolutely. Right? If it's mostly products, if it's product favored, then your K equilibrium would be greater than 1. And it stands to reason that if the reaction is reactant favored, that means that this number would be bigger, and you'd end up with a K equilibrium. So that in that case, your K equilibrium would be less than 1. And don't worry, we have this summarized on a slide. Well, what's the relationship between equilibrium constant and delta G of our reaction? And it's shown right here. We have delta G is equal to the negative of RT times the ln, or the natural logarithm, of the equilibrium constant. And that's another formula that you would have seen in general chemistry too. And so K equilibrium, delta G, delta H, delta S, those are all thermodynamic terms. They only describe the relative stability of reactants and products. It has nothing to do with the rate at which they are formed. So I want you to get that straight. There's a big difference between thermodynamics and kinetics that we've got to be aware of. What we're talking about right now on this slide is thermodynamics. If your K equilibrium is greater than 1, sure, your products are going to be favored. Let's think about it. If your ln, if you're taking the natural logarithm of a number that's greater than 1, that gives you a positive number. You take a positive multiplied by a negative, and you end up with a negative delta G. Okay, so mostly products gives you a negative delta G. If the converse happens, if you have a K equilibrium that's less than 1, take your calculator, take any number less than 1, take 0.5, and then take the natural logarithm. You get a negative number. So negative times a negative would give you a positive delta G. But again, these things don't have anything to do with the rate of the reaction. The way the book describes this is he says, well, an explosion is a spontaneous reaction. It happens really quickly. But diamonds being converted into graphite is also a spontaneous reaction. However, it is extremely slow. And so again, what we're talking about here is whether the reaction will be spontaneous or not. And we're going to get into reaction rate in just a moment. So a little summary of some of the things that we've covered. Let's take a look. This is kind of a summary in a way. First point, if delta G is negative, mostly products. If delta G is positive, then it's going to be mostly reactants. In order for a reaction to be useful, you got to have a delta G that's negative. Otherwise, you're going to have mostly reactants. That's not really useful. And this, we have a table. It's table 6.2 that really shows you how a small difference in Gibbs free energy, table 6.2, can have a huge impact on the ratio of reactants to products. I have that table in the slides. Just give me a second and we'll get there. And, you know, after the first time I taught this class, I put this in here years ago just to remind you of the laws of thermodynamics. And this is just kind of a Sparks Notes version of the laws of thermodynamics. But number one, energy can't be created or destroyed. Two, entropy, always increases. And the disorder of a perfect crystal at 0 degrees Kelvin is 0. So let's move on and take a look at that table, 6.2. And, you know, there's nothing really that you need to memorize in this table or anything. The bottom line is that if you just look at small changes in free energy, small changes in Gibbs free energy, let's say we go from, from 0, a delta G of 0 means you're at equilibrium. Your K equilibrium is 1. So that means you've got a 50-50 mixture. But if you just go down to -6 kilojoules per mole, we have 90% products. So that's a pretty useful reaction. Then if you decrease that by 5 and then 6, you go from 9 to 99 and 99.99%. So small changes in free energy have huge consequences with respect to the amount of products that we can get in our reaction. Well, let's take a look at a practice problem. That's quite a bit of me talking. So let's put on our thinking cap here for a second, see if we can solve this problem. This one comes straight out of our textbook. It's question 6.6. You might want to grab a calculator, maybe not. Depends on the person. Let's see if we can solve these questions. First one says, in each of the following cases, use the data that they gave you to determine whether or not the reaction favors reactants or products. What's going to be favored here? So let's look at the first one. A reaction for which the delta G is positive 1.52 kilojoules per mole. What's going to be favored there? Reactants or products? Can anybody tell me the answer to A? I'm just looking for a word, reactants or products. Delta G is positive. Yeah, absolutely. Absolutely. Thank you. So it's going to be mostly reactants if my delta G is a positive value. Reactants. There we go. What about if your K equilibrium is 0.5? My K equilibrium is 0.5. What would that be? Reactants or products? Yes, absolutely. It's also going to be reactants. So I'll put that in here, reactants. Remember that delta G was equal to the negative RT times the ln of K. If you take 0.5 and you take the ln of it, you get negative 0.693. So you take a negative number times negative RT ln K. That gives you a positive number. And so your delta G is going to be equal to the positive number. Anyhow, I guess you knew that already. C. Let's see C, shall we? A reaction carried out at 298 Kelvin, so that's 25 degrees Celsius, for which the delta H is positive 33 kilojoules per mole, and delta S is 150 joules per mole Kelvin. Well, joules and kilojoules aren't going to work together, so we have to either convert the kilojoules to joules or the joules to kilojoules. I'm going to convert the positive 33 kilojoules into joules. Does anybody know how many joules are in 1 kilojoule? It's not a trick question. How many joules in 1 kilojoule? What's the kilo mean? Yeah, thanks, Kiana. Exactly. Zoe, everybody, Clinton, you got it all right. So we could also say that our delta H is equal to 33,000 kilojoules per mole. And let's use the formula. So for C, we're going to use the formula delta G is equal to delta H minus T delta S. This is a formula that you've got to memorize as a chemistry student. Oops. Yeah, there we go. 33,000 kilojoules per mole subtract T delta S, so 298 Kelvin times 150 joules per mole Kelvin, like that. So I got my calculator out here. We see that Kelvin and Kelvin cancel. And when we do that, we get that delta G is equal to negative 11,700 joules per mole, or negative 11.7 kilojoules per mole. Well, I think you follow me on the answer. If the delta G is negative, then it's going to favor the products. So we'll scribble that down here. Products. We've got more products. Let's see. D. Oh, we really got a lot of questions in here. D says what? An exothermic reaction with a positive value of delta S of the system. So let's try that one. Same formula. Delta G is equal to delta H minus T delta S. T delta S. That's better. So if it's exothermic, that means that my delta H is a negative number. Then I'm going to subtract T is always a positive number. And then I've also got a positive value for my delta S. So that means you've got a negative, subtract a positive. And when you take a negative and you subtract a positive, you always end up with a negative number. And if it's a negative number, that means it's going to favor the products. So we'll scribble that in here. Products. Is there another one? Yep, there is. Let's try this one. E. Now we've got an endothermic reaction, so our delta H is positive, and a negative value for delta S of the system. So give that a try. So delta H minus T delta S. Put a lot of parts in here. So delta H is going to be positive, right? So we've got positive, and then we subtract a positive number multiplied by a negative value. So that means you've got the positive, subtract a negative. So that's the same thing as taking a positive and adding something to it. So that means you'll always get a positive number. That means that it's going to favor the reactants. Boom. There we go. Is everybody with me on that problem? Again, it's just kind of a quick run through of, do we understand the formula delta G is equal to delta H minus T delta S? Do we understand how K equilibrium relates to free energy? I didn't go into all the details that you would have gone into in Gen Chem 2. If you need to go back and review that, do it. But I've covered the crux of what you need to know, or everything that you need to know for this class, for the first 4 sections. Well, that covers everything up to equilibria. And now we're going to turn our attention to kinetics. I was kind of getting ahead of myself there a minute ago. And I said, hey, do you remember doing this? Rate is equal to rate constant multiplied by A to the power of X and B to the power of Y and all that good stuff. And remember, you had to determine X and Y experimentally. Who remembers doing that, just doing that in Gen Chem 2? Determining a rate law. And the rate, exactly, the order with respect to a reactant. Okay, so the good news is you're not going to have to work out any rate laws in organic chemistry. That's a Gen Chem 2 thing. Don't worry about it for this class. You just kind of need to understand like what rate is and the factors that affect rate. And I know that you all remember first order, second order, third order reactions. The good news is in this class, we're really only going to look at first and second order reactions, and that's about it. A third order reaction will come up maybe once or twice in the entire breadth of organic chemistry, or the entire content of organic chemistry 1 and 2. All right, let's cover a few more sections here before we take a quick break. And then, let's talk about kinetics for a few minutes. And you know what? One of the things I like about teaching kinetics is it's nice to teach something that's, I wouldn't say that chemistry, there's much in chemistry that's completely intuitive, but if there's one thing that I could say about organic chemistry that students usually find intuitive, usually it's kinetics. Students usually connect the dots with kinetics anyhow. So where are we? We said the sign of delta G tells us whether the reaction is spontaneous. If it's negative, it's spontaneous. If it's positive, it's not. Cool. Then we said, okay, Well, just because the reaction has a negative delta G, it doesn't tell us whether it's going to happen quickly or slowly. In other words, it doesn't tell us anything about the rate of the reaction whatsoever. And that's what we're talking about when we're talking about kinetics, the rate of reactions. So some spontaneous processes are fast, like an explosion. However, there are spontaneous processes, and I mentioned this one a few minutes ago. Diamond being converted into graphite, it's spontaneous, man. The delta G is negative. However, it takes millions of years. So yeah, it might be spontaneous, but it's kind of a useless reaction because it takes so long. The reaction rate is a function of the number of molecular collisions, right? Molecules have to collide, and in order for a reaction to occur, and the rate is a function of the number of those collisions over a given period of time. And what are those collisions going to be affected by? They're going to be affected by a whole holy host of things. First of all, the concentration. I mean, you saw that when I wrote out that formula. For example, let's say we say rate is equal to K multiplied by the concentration of A. Well, you can clearly see that rate is directly proportional to A. It is affected by concentration. That's what this bracket means. The square brackets means concentration here. Okay, so that's something you would have seen before. What about activation energy, temperature, geometry, and sterics? I don't know if you remember the Arrhenius equation. So the Arrhenius equation that you would have seen in general chemistry too, which is K, our rate constant, is equal to A, the pre-exponential factor, multiplied by e to the power of negative EA over RT. And so we see that the rate of our reaction, right, because this is our rate constant, is clearly affected by the activation energy. It's right there in the formula. It's also affected by the temperature. That's also there in the formula. And then the whole geometry and sterics thing, that's actually worked into this thing here, which I said is the pre-exponential factor. And then finally, the rate of reaction is also affected by the presence of a catalyst. Do we have a catalyst in our reaction? Generally speaking, it's going to increase the rate of the reaction. The reaction is going to occur at a faster rate. Well, I think this would be a good point for us to take a quick break, and then we're going to come back and we're going to get into these factors in more detail. So we're going to start out by looking at the concentration of reactants and how that affects the rate of reaction. And we're also going to talk about order of reaction. And so if you remember the whole exponent thing here, let's imagine that this number, or this x, if x was 1, that would be a first order reaction. If x was 2, that would be a second order reaction, so on and so forth. So we're going to come back in a few minutes and we'll discuss that.